All right. So we are going to continue on with gas phase chemistry. I'm going to finish out chapter 13 today. So far, we have that. Okay, that's our combined gas law. That was the very first day. The different components and then using the whole gas law. So that's two different situations. Okay, so we have starting conditions, final conditions. We're given everything but one, algebra. Okay. And then we moved on to the ideal gas law. E equals nRT. That doesn't have two different conditions. It's for calculating one condition. Pretty much the same thing. You get all but one. Remember, R is a constant, so you always know that. So those are pretty much just kind of, here's some information, throw it in the equation. Today, I'm going to start into some stoichiometry using gas. So this one, today will be a little bit more read and interpret, okay? Rather than just, hey, we're going to throw something in there. Okay? But yeah, so. Question. When doing anything with stoichiometry, what is the first thing that we need to do?
Balance the equation.
Balance the equation. Very good. Okay. And that is still true when dealing with gas phase stuff. Okay. If we're doing stoichiometry, we must have a balanced equation. Okay. You have to. Okay. Now, the book gives us this equation. Hydrogen, oxygen, you react them together, you're going to get water. Now, all of these are actually in the gas phase. All of them are going to be in the gas phase. So, we know 2 moles plus 1 mole gives us 2 moles. Here's the nice thing with working with gas. We can actually translate that straight to liters. So 2 liters of hydrogen plus 1 liter of oxygen will produce 2 liters of water. Okay. So why can we say that? Why can we say that? And it comes back to Avogadro's principle. Now, when we discussed Avogadro's principle, we said, so 1 mole of any gas at STP, 22.4 liters. Okay. Well, how does that apply here? Well, what this tells us is that it doesn't matter what gas you're dealing with. It just matters what the conditions are. Okay. You take any gas, and as long as they are under the same conditions, they're going to take up the same volume. Okay. Now, when you mix these, okay, they're going to be under the same conditions, right? is it possible to have one container where the pressure and temperature are different for the hydrogen and the oxygen? No. Okay. If they're in the same container, they have the same temperature and they have the same pressure, which means an equal volume has an equal number of particles, because we know from Avogadro's principle. Okay? Avogadro's principle tells us it only matters how many particles you have, not what type of gas. So, we can legitimately, this is a legitimate thing to do in chemistry, 2 liters of hydrogen, 1 liter of oxygen. Okay? That is stoichiometry. Okay? It's not breaking the rules at all. It's not simplifying it too much. It follows all the rules. Okay? So when dealing with gases, all you have to do, balance the equation, and then those can work out as not just moles, but liters as well. Okay? And we can use that as one of our conversion factors. Okay? So how do we do that? Well, let's look at example problem 7 right here in the book. It's on page 461. So what volume of oxygen gas is needed for the complete combustion of 4 liters of propane gas? Assume that pressure and temperature remain constant. Now, does it matter what pressure and temperature we're working with? It says they're constant. Does it matter? Should we pick one? It actually doesn't matter. Remember, as long as everything is in the same container, it's all going to be under the same temperature and pressure. And so we can do, using Avogadro's principle, just deal with volumes. And temperature and pressure don't matter, because we know that at that temperature and pressure, we have 4 liters of propane gas. So if we're going to use the same temperature and pressure, all we have to do is some very, very simple conversions. Now, of course, we need a balanced equation to do this. So we're dealing with the combustion of propane gas, and it tells us that propane gas is C3H8. And we know that for combustion, we need oxygen, and we're going to get carbon dioxide and water. Okay? Now, these are all going to be in the gas phases. Like I told you at the beginning of the year, sometimes I'm really bad about putting the phases in my equations. Sorry. Anyway, is this balanced? No, it's not. So we need to do a little bit of balancing. Okay. It's not too bad. So we have 3 carbons. Put 3 carbons here. Okay. So now we have 3 carbons on both sides. H8. So we have, we put 4 right there. Then we have 8. Now we have 6 oxygen, plus another 4 oxygen is 10. So we put a 5 right there. Okay. It's really not too bad. So now that we have that, we start with what we know. So we have 4 liters propane. And we know that for every 1, because there's a 1 right there, so 1 liter propane, we're going to use 5 liters of oxygen. Propane has been eliminated. We're left with liters of oxygen, which is exactly what we want. This is a pretty straightforward problem. We need to use up 4 liters of that. For every 1 liter, we need 5 liters. So $20. Okay. It's just straightforward stoichiometry. Like honestly, in volume to volume problems, they're exactly like mole to mole problems. If it had said you have 4 moles of propane, how many moles of oxygen do you need? It's the same work. Okay? We're just taking advantage of the fact that at the same temperature and pressure, we can go straight from moles to liters. Okay. Now, of course, we can't leave it that simple. We need to do a little bit more. Okay. But it really isn't that bad. There's no real new concepts in this section. It's just taking things that you've learned and putting them together in a new way. Okay. Which can sometimes be a little bit intimidating. But overall, this shouldn't be too bad. Because now we're going to throw in the whole mass thing. Okay. So let's look at example problem 8, a volume mass problem. So it says ammonia is synthesized from hydrogen and nitrogen. Look at that. This one even gives us the balanced equation. Isn't that nice of the problem? To give us the balanced equation. Okay. If 5 liters of nitrogen reacts completely with hydrogen at a pressure of 3 atmosphere and a temperature of 298 Kelvin, how much ammonia in grams is produced? So, we have our balanced equation, and it gives us liters of nitrogen and a pressure and a temperature. Okay. Now, to be completely honest, there are multiple ways that you can attack this problem. Okay. We're going to go through the way that this example sets it out, and then we'll talk about some of the other ways that you could have done it. Doing it the way that this example gives, it'll get you the right answer every time. So you can do that. Anyway, the first thing that the problem does is it wants us to convert how much ammonia we're going to get based off the fact that we have 5 liters of nitrogen. And that is just like we did on the last problem. Okay. So if we have 5 liters of nitrogen, and for every 1 liter of nitrogen, we're going to create 2 liters of ammonia. How many liters of ammonia are we going to create? Can you do that math in your head? 5 times 2. Take a minute. Figure it out. It's 10. Okay. So you have 10 liters of ammonia. Now at this point, they pull out the ideal gas law. Okay. Now, in the problem, it tells us our pressure is 3 atmospheres. It also tells us our temperature, 298 Kelvin. So now we need V, N, and R. What's our volume? 10. Okay. 10 liters of ammonia. Okay. What's N? Okay, so that's what we're trying to find out. Okay, that's what we're trying to find out. And R. Okay. So why did we pick that value of R? Because the pressure is in atmospheres. So. Okay. Now we can rearrange for N. We get that. Okay. And now we can fill in. Cancel out. We're left with 1 over 1 over mole, which is exactly what we want, because that's just moles. And now we just put that in the calculator. Yeah, that's all we have to do is put that in the calculator. And that gives us 1.23 moles. Okay. And then all we have to do is change from moles to grams. Okay. So 1 mole of ammonia is 17.04 grams per mole. So we take this, 17.04 grams in 1 mole, cancel out, multiply that, and we get 21.0 grams. Okay. So, nothing in there was new. Okay. There was no new concepts in there. It was just putting together the things that you already know. And we're pulling them all together and we're putting them together to form, to figure this out. Okay. Now this, granted, this is what we talked about at the beginning of class, but it's really straightforward, so that one shouldn't be too bad. Okay. So we've gone from 5 moles here to 10 moles here. We've taken that, or 10 liters. See, then I said moles. So 5 liters to 10 liters. So we have 10 liters. We can put that with the other pieces that they give us in the problem into our ideal gas law, which tells us how many moles there are. And then we take that number, turn it into grams. Okay. So like I said, there are multiple ways that we can attack this problem. Okay. And honestly, any one of them is valid. Okay. I know that there are some teachers that say if you don't do it my way, it's wrong. I don't believe in that. I believe that there are plenty of different ways that you can do something as long as all of the steps are valid. There's no reason to say it doesn't work. Okay. For example, we could go and take this 5 liters and put it into our ideal gas law. And that would tell us how many moles of nitrogen we're working with. And then we could go how many moles of nitrogen to moles of ammonia using this same conversion right here. And then do that. Okay, that's valid. Okay? It's a matter of where do you want to use the ideal gas law. Okay. Now, all of these methods might, like one of them, the answer was 21.0. One of them, just with rounding and stuff, it might give you a 21.1. Okay, 1/10 of a gram in this class, not a big deal. Okay. So you could have done that. Also, we did mention that if you need to go to mass, sounds like, or at Catholic church or something, if you need to go to mass. Anyway, number N, okay, did I write that backwards? I always forget which one is supposed to be capital.
I think we have to do it.
Yeah,
I thought it was doing it.
little m is supposed to be on top. It looked weird to me, that's why I was double checking. Because we have the actual mass, which is going to be the little m, divided by the molar mass, which is capital M. Okay? So we could have, get rid of this, could have said, all right, n equals that, but we know that capital M is 17.04 grams per mole. So then we can substitute this in here. And then solve for M. And then we just have to pull those things in, now to go straight to grams instead of going to moles and then grams. Okay. Is any one of those things better than the other? Not really. It's a matter of what makes sense to you, and can you get from point A to point B? Okay. For example, if I wanted to come here and drive to the airport, okay, there's a bunch of different ways that'll get me there. And there are different ways that people will prefer. One might be a little bit faster, but they all get you there. Okay. So I'm more concerned that you get there eventually rather than that you get there using my way. Okay. Let's do another example like this. Because even though none of it's really new material, there are a lot of moving parts. So let's just do another example, make sure that everyone feels comfortable. So if we look at, no, we'll just do 42 here on page 463. Ammonium nitrate is a common ingredient in chemical fertilizers. You can also use it to make a bomb, just by the way. You can. I don't know why you're looking at me like that. So, use the reaction shown to calculate the mass of solid ammonium nitrate that must be used to obtain 0.100 liters of dinitrogen monoxide gas at STP. Okay. So it gives us our balanced equation. So we've got our ammonium nitrate. Now this one's solid. Okay. And that breaks down into dinitrogen monoxide and water. Both of those are gases. Okay. So we want to know the mass of solid ammonium nitrate that must be used to obtain 0.100 liters of dinitrogen monoxide gas at STP. So we want to get that. Okay. Question. Can I use the conversion factor of liters to liters here?
Oh, no.
No, I can't. Why not?
Oh, it's not that. Oh.
It's a solid. If you're going to go liters to liters, you have to be both in gas form. Okay. So that limits the ways we can get there. Okay. But we can still get there for sure. Okay. Now, if it were me, since I can't go liters to liters, the first thing I would do is take this and put it into my ideal gas law. Now it tells us we want to have this volume at STP. Okay. So since we have STP, we know that we have 1 atmosphere and 0 degrees Celsius, which is 273 Kelvin. We know we have that volume. So obviously, what we're looking for is N. Okay. We didn't even need to know that ahead of time. We just needed to start putting in what we had. And we'll figure it out. Okay, now we're in atmosphere again. So we're going to use that value of R. So if we rearrange to solve for N, then we can say, okay, we've got 1 atmosphere times 0.100 liters divided by R times T okay. So we can go to our calculator, we can put that in. It's always nice at STP because pressure is 1 and multiplying by 1 is always really easy. Yeah. And so N is that's how many moles of dinitrogen monoxide we need to get 0.100 liters at STP. Okay, so now that we have moles, now we can use our stoichiometry. Okay. Now this is nice because guess what? It's a one-to-one relationship. So if we need to have 0.00446 moles of dinitrogen monoxide, how many moles of ammonium nitrate do we need? One-to-one. It's the same, right? So we need to know, the problem is asking, the mass of solid ammonium nitrate. So what is the mass in grams of this many moles of ammonium nitrate? Well, you go to our periodic table. And we see nitrogen, 14.007, okay, plus, well, we've got two of those nitrogens, so plus another one. And then we're going to have four hydrogens, okay, 1.008, four of those, and then three oxygens, okay, 15.999. And that gives us 80.043 grams in 1 mole. Moles cancel out, multiply. And oh look, I even got the same answer as the book. That's always comforting. So, 0.357 grams of ammonium nitrate. Once again, nothing new. It's just putting things together, okay? Putting things together. That is going to be a pattern that you'll see several times throughout this class, where the first couple sections in the chapter introduce some new concepts, give you some new skills, and then the last section of the chapter says, okay, let's throw it all together. Okay. So, any questions about what we've done today? It's the ideal gas law plus a little bit of stoichiometry. So we're taking everything that we learned in stoichiometry and we're saying, hey, we can work with gases as well. Okay. So remember how at the first day back where I said, I'm not going to directly ask you questions about the first semester, but you might still need to know some of the concepts. That's this. Okay. So I'm not going to ask you the same types of stoichiometry questions, but do you still need to know stoichiometry? Yes. But any stoichiometry questions you run into on a test, you're going to want to use the ideal gas law. Okay. We don't use the combined gas law with stoichiometry because they're all under the same pressure and temperature. Okay. There's no initial conditions and final conditions. The only equation that you're going to want to use with gas stoichiometry is the ideal gas law, because they're all under the same conditions from start to finish is what we assume. Okay? In real life, the conditions change, okay? But we're going to assume that they don't for this class. Okay. And that's the end of chapter 13. So, the end of chapter 13. It does have a little paragraph about how this is used in the real world. Basically, just like we said with stoichiometry, you want to make sure that you're not wasting a bunch of materials in the real world. So you want to get the ratios where you need them. But you already knew that. So I'll let you get started on some homework.